Hello there and welcome to the Sleepless Scientist. Tonight, we're traveling far from Earth, out past Mars and Jupiter, to a world that has captivated humanity for centuries. A planet wrapped in rings of ice and shadow, spinning silently in the cold depths of space. Saturn, the jewel of the solar system, a giant made of gas and mystery, orbited by dozens of moons, each with its own story to tell. Tonight, we'll drift through its storms, glide along its rings, and visit its distant moons. We'll explore the science, the beauty, and the quiet wonder of this magnificent world. So settle in, let your thoughts slow, and let's journey together to Saturn. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The jewel of the solar system. Among all the planets that circle our sun, none captures the imagination quite like Saturn. It's not the largest, not the closest, not the most colorful, but it is, without question, the most beautiful. The rings that encircle it are so vast, so delicate, that they seem almost impossible, like something borrowed from a dream. From Earth, through even a modest telescope, Saturn appears as a golden sphere wrapped in brilliant bands of light. Ancient astronomers had no name for what they saw. They only knew it was different, special. For centuries, Saturn stood alone in its elegance. No other planet came close. Even now, with all we've learned, with all the worlds we've discovered beyond our solar system, Saturn remains unique. Its beauty isn't loud or demanding. It's quiet, patient, a reminder that the universe can be both vast and delicate at once. A jewel hanging in the velvet dark, waiting for us to notice. And when we do, when we pause long enough to really see it, we remember why we look up at all. The first glimpse through a telescope. In the year 1610, an Italian mathematician named Galileo pointed a small telescope toward the night sky. He had already seen moons circling Jupiter, craters on our own moon, and stars invisible to the naked eye. But when he turned his gaze to Saturn, he saw something that didn't make sense. The planet wasn't round. It had shapes on either side, like handles or arms. He sketched what he saw, confused and fascinated. His telescope wasn't strong enough to reveal the truth. What he was seeing were the rings, but from his perspective, they looked like separate objects attached to the planet. He called them ears. For 2 years, he watched Saturn, trying to understand. Then, in 1612, the rings seemed to vanish. Galileo was baffled. He didn't know that Saturn's rings are so thin that when seen edge on, they disappear from view. He never solved the mystery in his lifetime, but his curiosity opened the door, and others would walk through it. The wonder that amazed Galileo. Imagine being Galileo in that moment. You've built one of the first telescopes in human history. You've discovered that the moon has mountains, that Jupiter has moons of its own. You're seeing things no human has ever seen before. And then you point your telescope at Saturn, and it's wrong. The planet doesn't look like a planet. It looks like 3 objects fused together. Galileo wrote letters to his contemporaries, describing what he saw. He was careful, precise, but also humbled. He knew he was looking at something beyond his understanding. He even wrote in Latin, in a kind of code, so that if someone else discovered it first, he could prove he'd seen it too. But no one else knew what it was either. For decades, Saturn remained a riddle, a world that refused to fit into the neat categories of astronomy. And in that refusal, it became more than just another planet. It became a mystery worth solving. The planet with ears, an ancient mystery. For decades after Galileo's first observations, astronomers struggled to explain Saturn's strange appearance. Some thought the planet had 2 large moons, one on each side. Others believed it was surrounded by some kind of solid shell. The ears theory persisted for years. Through better telescopes, Saturn's shape seemed to change. Sometimes the ears were visible, Sometimes they disappeared. Sometimes they tilted at odd angles. It was maddening. How could a planet change shape? In 1655, a Dutch astronomer named Christian Huygens built a more powerful telescope. He observed Saturn carefully over many months, and slowly the truth began to emerge. Huygens proposed that Saturn was surrounded by a flat ring, a thin disk that didn't touch the planet. It was tilted at an angle, which explained why it seemed to vanish and reappear. He published his findings in 1659, encoded in an anagram to protect his discovery. When decoded, it read, "It is surrounded by a thin flat ring, nowhere touching, inclined to the ecliptic." The ears of Saturn were finally understood, and the real mystery had only just begun. The discovery of the rings. Huygens' discovery was revolutionary, but even he didn't fully understand what he was seeing. He thought the ring was solid, a single unbroken structure. It wasn't until the late 1600s that astronomers like Giovanni Cassini observed gaps in the rings. Cassini discovered the largest gap, now called the Cassini division, and realized the rings weren't one solid piece. They were multiple structures, somehow separate, yet together. Over the next 2 centuries, scientists debated the nature of the rings. Were they liquid, solid, gas? In 1859, physicist James Clerk Maxwell proved mathematically that the rings couldn't be solid. They had to be made of countless small particles, each orbiting Saturn independently. Observations later confirmed this. The rings were made of ice and rock, billions of fragments ranging in size from dust grains to boulders, all circling Saturn in delicate, precise orbits. It was a dance of gravity and motion, stable yet fragile, and it was more beautiful than anyone had imagined. The gas giant beyond Jupiter. Saturn is the second gas giant in our solar system, orbiting just beyond Jupiter. While Jupiter is often called the king of planets, Saturn is its quieter, more graceful sibling. Both are massive worlds made mostly of hydrogen and helium. Both have no solid surface, but where Jupiter is wild and stormy, Saturn is serene. Its atmosphere is calmer, its colors more muted. The two giants formed in the early days of the solar system, more than 4.5 billion years ago. They were born from the same swirling disk of gas and dust that created the Sun. But Saturn formed farther out, where temperatures were colder and materials were scarcer. It grew large, but not as large as Jupiter. It developed rings, but Jupiter's rings are faint and thin. Saturn and Jupiter are siblings, yes, but each took its own path, and in doing so, they became two of the most fascinating worlds we've ever studied, each beautiful in its own way, each a reminder of how diverse planets can be. The sixth planet from the Sun. Saturn orbits about 1.4 billion kilometers from the Sun. That's nearly 10 times farther than Earth. At that distance, sunlight is weak and cold. The energy that reaches Saturn is less than 1% of what reaches us. To stand on one of its moons and look up at the Sun would be to see a bright star, nothing more, a distant point of light in a black sky. Saturn's orbit is vast. It takes nearly 30 Earth years to complete a single journey around the Sun. For most of human history, it was the farthest known planet. Ancient astronomers could see it with the naked eye, a faint golden dot moving slowly against the stars. They named it after the Roman god of time and agriculture. Slow, patient, distant, the name fit. Even now, with spacecraft and telescopes that can peer across the universe, Saturn remains a remote and mysterious world, a giant that drifts in the outer dark, wrapped in rings and silence. The second largest world in our system, Saturn, is enormous. Its diameter is about 120,000 kilometers, nearly 10 times wider than Earth. If Earth were a marble, Saturn would be a basketball. But despite its size, it's not the largest planet in our solar system. That title belongs to Jupiter. Still, Saturn is vast beyond comprehension. You could fit more than 760 Earths inside it. Its volume is staggering. Its mass, equally impressive. And yet, for all that size, Saturn is surprisingly light. It's made mostly of hydrogen and helium, the lightest elements in the universe. Its density is so low that theoretically, it could float in water. Of course, you'd need an ocean the size of a solar system to test that. But the fact remains, Saturn is a giant that weighs less than it should. A world of paradoxes. Massive, yet light. Beautiful, yet violent. A reminder that size and weight don't always go hand in hand, and that the universe is full of surprises. The beauty that defies description. There are images of Saturn taken from spacecraft, from telescopes, from Earth. Each one is breathtaking. The rings catch the light in ways that seem almost unreal. Thin bands of ice, glowing against the darkness. The planet itself, pale gold and cream, striped with faint clouds. Its moons scattered around it like jewels. Scientists can describe Saturn in numbers. Its mass, its diameter, its orbital period. But numbers don't capture what it feels like to see Saturn for the first time. That quiet awe, that sense of wonder. Poets and artists have tried to put it into words, into paintings, into music, but Saturn resists easy description. It exists in a realm beyond language. It's a world that asks you to stop, to pause, to simply look, and in that looking, to remember that the universe is full of beauty we'll never fully understand. Saturn doesn't demand your attention. It waits, and when you're ready, it shows you something unforgettable, the pale golden glow in the night sky. From Earth, Saturn appears as a steady, pale yellow point of light. It doesn't twinkle like stars do. Planets rarely do. Their light is reflected sunlight, not the burning fusion of distant suns. And because they're so much closer, their light is steadier. Saturn's glow is gentle, warm, even through light pollution. Even from a city, you can spot it if you know where to look. Ancient astronomers tracked its slow movement across the sky. They noticed that it didn't behave like the stars. It wandered. That's why the Greeks called planets wanderers. Saturn's motion was the slowest of all the visible planets. It drifted through the constellations, like a patient traveler. Nowadays, with apps and charts, it's easy to find Saturn, but there's still something magical about seeing it with your own eyes. That tiny dot of light, that distant world wrapped in rings, a reminder that we're part of something vast and beautiful, and that wonder is always there, waiting for us to look up. The composition of Saturn's atmosphere. Saturn's atmosphere is a thick blanket of gases wrapped around its core. About 96% of it is hydrogen, the simplest and most abundant element in the universe. Another 3% is helium. The rest is a mix of methane, ammonia, water vapor, and trace chemicals that give Saturn its subtle colors. These gases don't just sit still. They flow, they churn, they form clouds and storms. The atmosphere is divided into layers, each with different temperatures and pressures. Near the top, where sunlight reaches, temperatures can drop to -180 degrees Celsius. Deeper down, pressure and heat increase. The hydrogen begins to behave strangely, shifting between gas and liquid in a gradual transition. There's no clear boundary, no solid surface to land on. If you fell into Saturn's atmosphere, you'd just keep sinking through clouds and haze, into ever-increasing pressure and heat. Eventually, you'd be crushed, but before that, you'd witness one of the most alien environments in the solar system, a world made of air, the layers of hydrogen and helium. Beneath Saturn's visible clouds lies a vast ocean of hydrogen, not liquid in the way water is liquid. This is molecular hydrogen, compressed by immense pressure into a thick, dense fluid. It's a strange state of matter, neither gas nor quite liquid. As you go deeper, the pressure keeps rising. Thousands of kilometers down, something extraordinary happens. The hydrogen molecules break apart. Electrons are stripped away, and the hydrogen becomes metallic. It conducts electricity like metal, flows like liquid, and glows with heat. This metallic hydrogen layer is where Saturn's magnetic field is generated. Deeper still, scientists believe there's a core, solid rock and ice, perhaps 15 to 20 times the mass of Earth. But we're not certain. No spacecraft has ever descended into Saturn's interior. All we have are models, calculations, and observations from afar. The layers of Saturn are a mystery wrapped in mystery, and yet we keep looking, keep learning, keep unraveling the secrets of this quiet giant. The planet that's mostly air. It's strange to think of a planet being made of air, but that's essentially what Saturn is. No continents, no oceans, no ground to stand on, just layers of gas and liquid hydrogen stretching down for tens of thousands of kilometers. If you could somehow hover in Saturn's upper atmosphere, you'd see clouds below you, faint and golden. Above you, the blackness of space. Around you, winds howling at hundreds of kilometers per hour. It would be beautiful and terrifying in equal measure. Saturn is a reminder that planets don't have to be like Earth. They don't need oceans or mountains. They don't need solid ground. A planet can be a storm, a swirl of gas held together by gravity. A place where the rules are different, where solidity is replaced by flow, where the surface is just an illusion. And in that strangeness, there's a kind of elegance. Saturn is what it is, because of the conditions where it formed, and it's perfect in its own way. The weightless giant that could float in water. Here's a strange thought. Saturn, the second largest planet in our solar system, is less dense than water. Its average density is about 0.687 grams per cubic centimeter. Water, by comparison, is 1.0. That means if you could find a bathtub large enough, Saturn would float. Of course, no such bathtub exists, and Saturn would probably disintegrate before you got it anywhere near water. But the principle holds. Saturn's low density comes from its composition. Hydrogen and helium are the lightest elements in the universe, and Saturn is made almost entirely of them. Jupiter, by contrast, is denser. Its gravity has compressed its interior more tightly. But Saturn, farther from the Sun, gathered less mass. It's a gentle giant, a world of air and ice and cloud, a planet that defies our expectations of what a planet should be. And in doing so, it teaches us that the universe is more diverse and surprising than we could ever imagine. The fastest winds in the solar system. Saturn's atmosphere is in constant motion. Winds race around the planet at speeds that would obliterate anything in their path. Near the equator, wind speeds can reach 1,800 kilometers per hour. That's 5 times faster than the most powerful hurricanes on Earth. These aren't gusts. They're sustained, relentless streams of air flowing around the planet in great bands. The winds are driven by heat from Saturn's interior. Unlike Earth, which gets most of its energy from the Sun, Saturn generates heat from within. As the planet slowly contracts, gravitational energy is converted to heat. That heat rises, creating convection currents in the atmosphere, and those currents drive the winds. The result is a planet wrapped in jet streams, each one circling Saturn at different latitudes. The atmosphere is a machine, driven by heat and rotation, operating on a scale we can barely comprehend, and it's been running for billions of years. Steady, unstoppable, a storm that never ends. The jet streams that circle its surface. Saturn's atmosphere is divided into bands, each one a jet stream flowing east or west. These bands are visible as faint stripes in the planet's clouds. Some are light, some are dark. Each one represents a different layer of the atmosphere, moving at a different speed. On Earth, we have jet streams too, but ours are narrow and meandering. Saturn's are vast and stable. They circle the entire planet, driven by the heat from below and the planet's rapid rotation. The boundaries between these bands are turbulent. Winds collide, creating eddies and vortices. Sometimes, storms form at these boundaries, swirling masses of cloud that can last for months. Saturn's jet streams are a masterclass in fluid dynamics. They're shaped by forces we're only beginning to understand: Coriolis, effects, convection, differential rotation. It's chaos, but it's ordered chaos, and it's beautiful. From a distance, Saturn's bands look calm, but up close, they're rivers of wind, each one flowing with a power that could tear worlds apart. The planet that spins once every 10 hours. Saturn rotates quickly. A day on Saturn, measured from one sunrise to the next, lasts only about 10.5 Earth hours. That's one of the fastest rotation rates in the solar system. For such a massive planet, that speed is remarkable, and it has consequences. The rapid rotation creates powerful forces. The equator bulges outward, while the poles flatten. Saturn isn't a perfect sphere. It's an oblate spheroid, wider at the equator than from pole to pole. The difference is noticeable even in photographs. The planet looks squashed, like a ball pressed down from above. That flattening affects everything. The gravity at the equator is slightly weaker than at the poles. The atmosphere is stretched and pulled. The jet streams are shaped by the rotation, their paths dictated by the spinning of the planet beneath them. Saturn's rapid spin is part of what makes it so dynamic. It's a world in constant motion, never still, always turning. And that motion, combined with its size and composition, makes Saturn the magnificent planet it is. The flattened shape from rapid rotation. When you see a picture of Saturn, one of the first things you might notice is that it doesn't look quite round. It's wider than it is tall. The equator bulges outward, while the poles are noticeably flattened. This is a direct result of Saturn's rapid rotation. As the planet spins, centrifugal force pushes outward at the equator. The material there, mostly gas and liquid hydrogen, is flung outward. The poles, by contrast, experience no such force, so they remain closer to the planet's center. The result is a planet that's about 10% wider at the equator than from pole to pole. If Saturn spun even faster, it might tear itself apart, but it doesn't. It spins at just the right speed to maintain its shape. This flattening isn't unique to Saturn. Jupiter is also oblate. So are many other gas giants we've discovered orbiting distant stars. It's a natural consequence of rotation and gravity. A reminder that planets aren't static objects. They're dynamic, shaped by forces we can measure and predict. And in Saturn's case, those forces have created something extraordinary. The hidden core beneath the clouds. Deep beneath Saturn's clouds, beneath the layers of hydrogen and helium, there's likely a core. Scientists believe it's made of rock and ice, compressed under unimaginable pressure. The core might be 15 to 20 times the mass of Earth, but we don't know for sure. No spacecraft has ever descended into Saturn's interior. All we have are models based on the planet's gravitational field, its rotation, and the behavior of its magnetic field. Those models suggest that the core is small compared to the planet as a whole. It's buried under tens of thousands of kilometers of gas and liquid, and the conditions there are extreme. Pressures millions of times greater than Earth's atmosphere. Temperatures hot enough to melt most materials. It's possible the core isn't even solid. It might be a thick slush of rock and ice, compressed beyond recognition. We may never know for certain, but the fact that we can deduce its existence, that we can peer through layers of cloud and gas to understand what lies beneath, is a testament to human ingenuity. The metallic hydrogen deep inside. One of the strangest substances in Saturn's interior is metallic hydrogen. It's not a metal in the traditional sense. It's hydrogen, the lightest element, compressed so intensely that it behaves like a conductor. Electrons are stripped from the hydrogen molecules, creating a sea of charged particles. This happens thousands of kilometers below Saturn's surface, where pressures are extreme. The metallic hydrogen layer is vast. It makes up much of Saturn's interior, and it's responsible for one of the planet's most important features, its magnetic field. As Saturn rotates, the metallic hydrogen flows. That flow generates electrical currents, and those currents create a magnetic field that extends far into space. The existence of metallic hydrogen was predicted decades before we ever saw evidence of it. Scientists wondered what happens to hydrogen under extreme pressure. Now we know. It transforms. It becomes something entirely new, and in doing so, it powers one of the most beautiful phenomena in the solar system, Saturn's magnetosphere, a shield against the solar wind, an invisible force field protecting the planet and its moons. The source of Saturn's magnetic field. Saturn's magnetic field is weaker than Jupiter's, but it's still impressive. It extends millions of kilometers into space, forming a bubble called the magnetosphere. Inside this bubble, Saturn is shielded from the solar wind, the stream of charged particles flowing from the sun. The magnetic field is generated deep within Saturn, in the layer of metallic hydrogen. As the planet rotates, the metallic hydrogen flows, creating electrical currents. Those currents generate the magnetic field. It's the same principle that powers Earth's magnetic field, though on a much larger scale. Saturn's magnetic field is also unusually symmetric. Most planets have magnetic fields that are tilted or offset from their rotation axis. Saturn's field is almost perfectly aligned. Scientists aren't entirely sure why. It's one of the many mysteries surrounding this planet. But the magnetic field has consequences. It traps charged particles from the solar wind, creating radiation belts around Saturn, and it interacts with the planet's moons, generating auroras and radio emissions, a field of invisible energy, shaping the space around Saturn in ways we're only beginning to understand. The aurora that glows at its poles. Just like Earth, Saturn has auroras, shimmering curtains of light that dance across the poles. But Saturn's auroras are different from ours. They're larger, more powerful, and they glow in ultraviolet light, invisible to the human eye. These auroras are caused by charged particles from the solar wind colliding with Saturn's upper atmosphere. The magnetic field funnels these particles toward the poles, where they slam into gas molecules. The collisions release energy in the form of light. On Earth, auroras are mostly green and red, caused by oxygen and nitrogen. On Saturn, the auroras glow in ultraviolet, driven by hydrogen. They're constantly active, flickering, and shifting. Spacecraft like Cassini captured images of Saturn's auroras, revealing their structure and behavior. They're not just pretty lights, they're windows into the planet's magnetic environment. They tell us about the solar wind, the magnetosphere, and the interactions between Saturn and its moons. And they remind us that even in the cold, distant reaches of the solar system, beauty and science go hand in hand. The beauty of light dancing in its atmosphere. Saturn's auroras aren't the only light show in its atmosphere. Sunlight, reflecting off clouds, creates subtle gradations of color. Shadows cast by the rings add depth and contrast. And deep in the atmosphere, lightning flashes in massive storms. The interplay of light and shadow on Saturn is constantly changing. As the planet rotates, different features come into view. The rings shift from edge-on to fully open. The moons pass in front of or behind the planet, casting tiny shadows. It's a dynamic, ever-changing scene, and it's all driven by natural processes. Gravity, rotation, light. Saturn doesn't need artificial beauty. It doesn't need enhancement. It is, simply and profoundly, one of the most beautiful objects in the solar system. And every time we look at it, whether through a telescope or in images from spacecraft, we're reminded of that beauty. A beauty that exists for no reason other than the laws of physics. And perhaps that's the most beautiful thing of all. The storms that never end. Saturn's atmosphere is never calm. It's a world of constant storms, some lasting for months, others for decades. These storms form when warm gas rises from the interior, creating convection currents. As the gas rises, it cools and condenses, forming clouds. The clouds are whipped around by the planet's powerful winds, creating swirling vortices. Some storms are small, just a few hundred kilometers across. Others are massive, spanning thousands of kilometers. They appear as bright spots in Saturn's clouds, sometimes visible even from Earth. The storms generate lightning, thunder, and turbulence. They're chaotic, violent, and utterly fascinating. On Earth, storms are driven by the sun's heat, but on Saturn, the energy comes from within. The planet is still contracting, still radiating heat left over from its formation. That heat fuels the storms, and because there's no solid surface to slow the winds or disrupt the flow, the storms can last far longer than they ever could on Earth. Saturn's atmosphere is a machine that never stops, always churning, always creating, always in motion. The great white spot that appears every 30 years. Approximately once every 30 years, a massive storm erupts in Saturn's northern hemisphere. It's called the Great White Spot, and it's one of the most dramatic phenomena in the solar system. The storm appears as a bright white patch in Saturn's clouds. It grows rapidly, spreading across thousands of kilometers. Within weeks, it can encircle the entire planet. The storm is driven by convection. Warm gas from deep within Saturn rises to the surface, bursting through the upper cloud layers. It's like a geyser of heat and energy. The storm generates powerful winds, lightning, and turbulence. And then, after a few months, it fades. The energy dissipates. The clouds settle, and Saturn returns to its usual calm. The Great White Spot appears regularly because of Saturn's long year. The planet takes 30 Earth years to orbit the Sun, and the storm is linked to seasonal changes in the atmosphere. It's a reminder that even on a world without seasons in the traditional sense, cycles still exist, and sometimes those cycles produce spectacles that take our breath away. The lightning that flashes for days. In 2009, the Cassini spacecraft detected a massive storm in Saturn's southern hemisphere. It was a monster, spanning thousands of kilometers, and it was generating lightning. Not occasional flashes, but constant, sustained bursts of electrical energy. Some of the lightning bolts were more powerful than anything we've seen on Earth. The storm raged for months, producing lightning storms that lasted for days at a time. Radio emissions from the lightning could be detected from millions of kilometers away. Scientists called it a lightning storm, and it was one of the longest-lasting storms ever observed on another planet. Lightning on Saturn is generated the same way it is on Earth. Ice particles and clouds collide, creating static charge. That charge builds up until it's released in a massive discharge. But on Saturn, the scale is far greater. The clouds are thicker, the storms are larger, and the energy involved is immense. These lightning storms are a reminder of the raw power lurking in Saturn's atmosphere, a power that dwarfs anything we experience on Earth. The hexagon at the North Pole. At Saturn's North Pole, there's a feature that shouldn't exist, a perfect hexagon. It's not painted on the clouds. It's not an optical illusion. It's a real physical structure in the atmosphere, a six-sided jet stream, each side about 13,800 kilometers long. The hexagon was first discovered by the Voyager spacecraft in the 1980s. When Cassini arrived decades later, it was still there, unchanged, stable. Scientists were baffled. How could a jet stream form a perfect hexagon? Jet streams on Earth meander, they shift, they change. But Saturn's hexagon is stable, locked in place for decades at least. The answer lies in fluid dynamics. When rotating fluids interact at different speeds, they can form polygonal shapes. It's been replicated in labs, but the scale on Saturn is staggering. A hexagon, the size of two Earths, spinning at the pole. It's one of the most bizarre and beautiful features in the solar system, and it's a reminder that nature can create patterns more intricate than anything we design. The six-sided jet stream that shouldn't exist. The hexagon at Saturn's North Pole is a jet stream, a river of wind flowing around the pole at about 320 kilometers per hour. But unlike most jet streams, it has corners, 6 of them, arranged in a perfect hexagon. Each side is straight, each corner sharp. The hexagon is stable because of the specific conditions at Saturn's pole: the rotation of the planet, the flow of the atmosphere, and the interactions between different layers of wind, all combine to create this shape. It's a natural phenomenon, but it feels designed, mathematical, precise. Inside the hexagon, the atmosphere is relatively calm. Outside, the winds swirl chaotically. The hexagon acts like a barrier, separating the two regions. At the very center of the hexagon, there's a vortex, a swirling storm, much like a hurricane. But this storm has been raging for decades, possibly centuries. It's locked in place, spinning at the pole, surrounded by the hexagonal jet stream. The hexagon is one of Saturn's greatest mysteries, and one of its most captivating features: the perfect geometric storm. The hexagon isn't just a jet stream. It's a work of art, a geometric pattern etched into the clouds of a gas giant. The straight sides, the sharp corners, the symmetry, it all feels deliberate, intentional, but it's not. It's the result of physics, of forces and flows interacting in precise ways. The hexagon changes color with the seasons. During Saturn's winter, the North Pole is in shadow, and the hexagon is dark. During summer, it's bathed in sunlight, and it glows golden. The clouds within the hexagon shift and swirl, creating ever-changing patterns, but the hexagon itself remains stable, unchanging. Scientists have spent years studying it, trying to understand the forces that create it, and slowly, piece by piece, the puzzle is coming together. But even with understanding, the hexagon doesn't lose its magic. If anything, knowing how it forms makes it more beautiful, because it's proof that nature, left to its own devices, can create wonders beyond imagination. The calm eye within the chaos. At the center of the hexagon, there's a storm, a massive vortex, hundreds of kilometers across. It spins at the North Pole, locked in place by the forces around it. The eye of the storm is calm, just like the eye of a hurricane on Earth. But the winds around it are ferocious, whipping around at hundreds of kilometers per hour. This storm is unique. It's not moving. It's not drifting across the planet like storms usually do. It's anchored to the pole, spinning in place. Scientists believe it's been there for decades, possibly much longer. The storm is powered by heat from Saturn's interior. As warm gas rises, it feeds the vortex, keeping it alive. The storm generates its own weather. Clouds form, lightning flashes, and winds howl, a small circle of relative peace in the heart of chaos. It's a microcosm of Saturn itself, beautiful and violent, calm and chaotic. A reminder that even in the most turbulent places, there can be moments of quiet, and in those moments, we find clarity. The colors of Saturn's clouds. Saturn's colors are subtle, not the bold reds and whites of Jupiter, not the vibrant blues of Neptune. Saturn's palette is muted, cream and gold and pale yellow, with hints of brown and orange. These colors come from the chemicals in its atmosphere. Ammonia ice crystals form the upper clouds, giving Saturn its pale hue. Deeper down, clouds of ammonium hydrosulfide add shades of brown and orange. And even deeper, water ice clouds contribute faint blues and grays. But the colors are faint. Saturn's atmosphere is hazy, covered in a thick layer of aerosols. These particles scatter light, softening the colors and giving the planet its gentle glow. The haze is thicker at higher altitudes, which is why Saturn looks so uniform from a distance. But up close, the colors become more distinct. Bands of different shades circle the planet. Shadows cast by the rings add contrast and in certain wavelengths, hidden details emerge. Saturn's colors are a whisper, not a shout, but they're no less beautiful for it. The layers of ammonia and ice crystals. Saturn's clouds are arranged in layers, each one made of different chemicals. At the top, where temperatures are coldest, ammonia condenses into ice crystals. These crystals form thin, wispy clouds that give Saturn its pale appearance. Below that, in a slightly warmer layer, ammonium hydrosulfide forms thicker clouds. These clouds are brown and orange, though they're often hidden beneath the ammonia haze. Even deeper, where temperatures are warmer still, water ice forms clouds. These clouds are rare and difficult to see from above, but they exist. Each layer of cloud represents a different temperature and pressure, and as you descend through Saturn's atmosphere, the conditions change. The clouds thicken, the colors deepen, and eventually, the clouds give way to liquid, and then to the strange, dense hydrogen of the interior. It's a journey through layers of chemistry and physics, each one distinct, each one contributing to the overall appearance of the planet, and each one a reminder that Saturn is far more complex than it appears. The subtle hues of cream and gold. From Earth, Saturn appears as a pale golden dot. Through a telescope, that gold resolves into bands of cream and pale yellow. It's a gentle palette, soothing to the eye. The colors are soft, the contrasts low. Unlike Jupiter, which is bold and striking, Saturn is understated. The gold comes from sunlight, reflecting off the clouds, but it's filtered through the haze, diffused and softened. The cream tones come from the ammonia ice crystals in the upper atmosphere, and the faint browns and oranges, visible only in the best images, hint at the chemistry happening deeper down. Saturn's colors are a reflection of its composition, its temperature, and the way light interacts with its atmosphere. They're not dramatic, they're not flashy, but they're perfect. They suit the planet, calm, serene, beautiful, in a quiet way. And when you see Saturn through a telescope, when you catch that golden glow, it stays with you, a reminder that beauty doesn't always need to be loud. The shadows cast by its rings. One of the most striking features in images of Saturn is the shadow cast by its rings. The rings are so thin, so delicate, that they seem almost insubstantial, but they're solid enough to block sunlight, and when that light is blocked, it creates a shadow on the planet below. The shadow is a dark band across Saturn's clouds, a stark line that shifts with the seasons. When the rings are tilted toward the sun, the shadow falls near the equator. When the rings are edge-on, the shadow disappears. The shadow is a beautiful reminder of the relationship between Saturn and its rings. They're separate, yes, but also connected. The rings shape the light that reaches the planet, and the planet's gravity shapes the rings. It's a dance that's been going on for millions, perhaps billions of years. The shadow also tells us something about the ring's opacity. In some places, the shadow is dark and sharp. In others, it's faint and diffused. That's because the density of the rings varies. Some regions are thick with particles, others are sparse, and all of that information is written in the shadow, waiting for us to read it. It's one of the many ways Saturn reveals its secrets, through light and shadow, through the interplay of ice and sunlight. The planet tells its story. The rings, Saturn's greatest mystery. Of all Saturn's wonders, the rings are the most iconic. They're what makes Saturn instantly recognizable, what make it special. But despite centuries of study, the rings remain deeply mysterious. We know they're made of ice and rock. We know they're thin, incredibly thin, compared to their width. We know they orbit Saturn in precise, predictable patterns, but we don't know where they came from. We don't know exactly how old they are, and we don't know how much longer they'll last. The rings could be ancient, as old as Saturn itself, or they could be relatively young, only a few 100 million years old. Different lines of evidence point in different directions, and scientists continue to debate. What we do know is that the rings are beautiful, they're complex, They're dynamic, and they're one of the greatest natural wonders in the solar system. A structure so vast and so delicate that it seems impossible. And yet there it is, circling Saturn, waiting for us to understand the discovery of the ring's true nature. For decades after Huygens proposed that Saturn was surrounded by a ring, astronomers assumed it was solid, a single, unbroken structure. But observations kept revealing complications, gaps in the ring, variations in brightness. In the 1850s, James Clerk Maxwell tackled the problem mathematically. He asked, could a solid ring be stable? His calculations said no. A solid ring would be torn apart by gravitational forces. It would either collapse onto Saturn or break into pieces. The only way the rings could be stable, Maxwell concluded, was if they were made of countless small particles, each particle orbiting Saturn independently. It was a radical idea, and it was correct. Later observations confirmed it. The rings were not solid. They were a swarm, a cloud of ice and rock, held in place by gravity and motion. Maxwell's work was a triumph of mathematical physics. He'd solved the mystery of the rings without ever seeing them up close, and in doing so, he'd revealed something profound about the nature of planetary rings everywhere, the countless particles that form the bands. Saturn's rings are made of billions, perhaps trillions of individual particles. Each one is a tiny moon, orbiting Saturn according to the same laws of gravity that govern the planets. The particles range in size from specks of dust to boulders the size of houses. Most are made of water ice, pure and bright. Some contain rock and dust. The particles are packed closely together in some regions, sparsely in others. In the densest parts of the rings, particles are only a few meters apart. In the gaps, they're kilometers away from their nearest neighbors. And yet, despite the crowding, collisions are gentle. The particles are moving at similar speeds, in similar orbits. When they touch, they bounce off each other softly. It's a delicate ballet, choreographed by gravity, and it's been going on for as long as the rings have existed. Each particle follows its own path, but together, they create something magnificent. A structure visible from a billion kilometers away, a testament to the power of gravity and motion. The ice and rock, in perfect balance. The particles in Saturn's rings are mostly ice, bright, reflective water ice that catches the sunlight and glows. But there's also rock, silicate dust, carbon compounds, and other materials mixed in with the ice. The proportions vary across the rings. Some regions are almost pure ice. Others contain more rock and dust, which gives them a darker, redder hue. The ice particles are incredibly reflective. That's why Saturn's rings are so bright. They reflect more than 70% of the sunlight that hits them. It's one of the highest albedos of any object in the solar system. The ice is also very pure. It's cleaner than snow on Earth, and it's ancient. Some of the ice may have been part of the rings since they formed. Over time, the rings have been darkened by micrometeorite impacts and dust from Saturn's moons. But they're still bright, still beautiful. The balance between ice and rock, between purity and contamination, is what gives the rings their character, and it's what makes them one of the most studied structures in astronomy. The thinness beyond belief. Saturn's rings are vast. They stretch for hundreds of thousands of kilometers. The main rings span from about 7,000 kilometers above Saturn's cloud tops to more than 80,000 kilometers out. If you could see them edge on, they'd stretch farther than the distance from Earth to the Moon. But here's the astonishing thing. Despite their enormous width, the rings are incredibly thin. In most places, they're only about 10 to 30 meters thick. 10 meters. That's about 3 stories. Imagine a structure the size of a continent that's only as thick as a building. That's the scale we're talking about. If you made a scale model of Saturn's rings out of paper, the paper would be thicker than the rings should be. The thinness is maintained by the constant interactions between particles. Collisions damp out any vertical motion, Particles that drift above or below the plane are pulled back by the gravity of their neighbors. The result is a disk so flat, so thin, that it seems impossible, and yet it exists. A miracle of physics and gravity. The ring's only 10 meters thick. 10 meters. It's hard to wrap your mind around that number. The rings of Saturn, which span hundreds of thousands of kilometers, are in most places only about 10 meters from top to bottom. You could stack 3 cars on top of each other and reach from the bottom of the rings to the top. It's a testament to how finely balanced the system is. Any disturbance, any bump, and particles would start drifting up or down, but they don't. The rings are stable. The thinness also means the rings contain less material than you might think. If you gathered all the ice and rock in Saturn's rings and compressed it into a single moon, it would only be about 200 kilometers across. Tiny, compared to Saturn itself. The rings look massive because they're spread out, but in reality, they're a thin veil of ice surrounding the planet. Delicate, fragile, and yet they've persisted for millions, perhaps billions of years. A reminder that sometimes the most delicate things are also the most enduring. Saturn's rings aren't uniform. They're divided into several distinct regions, separated by gaps. The largest gap is the Cassini division, a dark band about 4,800 kilometers wide. It sits between the A ring and the B ring, the two brightest sections of the ring system. The Cassini division isn't completely empty. There are still particles there, but they're much sparser than in the main rings. The gap is created by gravitational resonances with Saturn's moons. Particles in the Cassini division orbit Saturn at a rate that's in sync with the moon Mimas. Every time Mimas completes 2 orbits, a particle in the gap completes 3. That regular gravitational tug pulls particles out of the gap over time. There are other gaps too. The Inky gap, the Keeler gap, each one carved out by the gravitational influence of small moons. These gaps give the rings their structure, their texture. They're proof that the rings aren't static. They're dynamic, shaped by forces we're only beginning to understand. And they're beautiful, adding complexity to an already stunning system. The Cassini division and its dark beauty. The Cassini division is one of the most prominent features in Saturn's rings. It's a dark band, a space where the particles thin out. From Earth, it looks like a gap, a void in the rings. But up close, it's more complex. There are still particles in the Cassini division. They're just less densely packed. And there are even faint ringlets within the division, narrow bands of particles that somehow survive, despite the gravitational forces trying to clear them out. The division is named after Giovanni Cassini, the astronomer who first observed it in 1675. It's a fitting tribute. Cassini's observations revealed that Saturn's rings weren't a single structure, but something more intricate. The Cassini division is about 4,800 kilometers wide. That's wider than the United States. And yet from a distance, it's just a thin line, a shadow in the rings. But that shadow tells a story of gravity and resonance, of moons and particles, of forces shaping the rings over millions of years. The Cassini division is more than just a gap. It's a window into the dynamics of Saturn's ring system, the faint fring at the edge. Beyond the main rings, past the A ring and the Cassini division, there's a faint, narrow ring called the Pfeff ring. It's one of the strangest structures in the entire ring system. The Pfeff ring is narrow, only a few hundred kilometers wide, but it's not smooth. It's twisted, braided, kinked. It looks like a rope that's been tied in knots. The Pfeff ring is shaped by 2 small moons, Prometheus and Pandora. These shepherd moons orbit just inside and outside the Pfeff ring. Their gravity tugs on the ring particles, keeping them confined to a narrow band. But the interaction also creates distortions. As the moons orbit, they pull the F ring into strange shapes. The result is a ring that's constantly changing. Images taken months apart show different structures, different knots and braids. The F ring is a laboratory for studying how gravity shapes ring systems. It's proof that even small moons can have a big impact, and it's one of the most photogenic features in the Saturn system. Delicate, intricate, and endlessly fascinating. The shepherd moons that shape the rings. Scattered throughout Saturn's ring system are dozens of small moons. Many of them are tiny, just a few kilometers across, but despite their size, they have a profound impact on the rings. These are the shepherd moons. They orbit within or near the rings, and their gravity shapes the structure around them. Prometheus and Pandora shepherd the Pfeff ring, keeping its particles confined. Pan orbits within the Encke gap, clearing out a path through the A ring. Daphnis creates waves in the Keeler gap, ripples that extend for hundreds of kilometers. The shepherd moons are like gardeners, tending the rings, keeping them organized. Without them, the rings would slowly spread out, diffusing into space. But the moons keep them in check. The relationship between the moons and the rings is complex. It's a dance of gravity, a constant push and pull. And it's one of the reasons Saturn's rings are so intricate, so detailed. Every gap, every wave, every structure has a story. And often, that story involves a small moon, quietly shaping the rings from within. The dance of gravity and ice. The rings of Saturn are a masterpiece of orbital mechanics. Every particle is in motion, following the laws of gravity. Particles closer to Saturn move faster. Particles farther out move slower. It's Kepler's laws in action, on a scale that's breathtaking. The particles don't just orbit, they interact. They collide, gently transferring momentum. They clump together, forming temporary aggregates that then break apart. They respond to the gravity of Saturn's moons, shifting their orbits in subtle ways. The result is a system that's constantly evolving. The rings aren't static, they're alive with motion, and that motion creates structure, waves, gaps, spirals, all emerging from the simple interactions between particles and gravity. Scientists call it self-organization, order arising from chaos. It's one of the most beautiful concepts in physics, and Saturn's rings are one of the best examples in nature. A reminder that complexity doesn't require a designer. It emerges naturally, inevitably, from the laws of physics, and when it does, it's stunning. The microscopic collisions that keep it stable. Saturn's ring particles are constantly colliding, not violently, but gently. Billions of collisions happening every second. Each collision is tiny, insignificant on its own, but together, they keep the rings stable. When particles collide, they lose energy. That energy is dissipated as heat. The result is that particles that are moving too fast slow down. Particles that are drifting out of the ring plane are nudged back. It's called collisional damping, and it's what keeps the rings so thin. Without these collisions, the rings would quickly become thick and diffuse. Particles would drift up and down, spreading out into a cloud. But the collisions prevent that. They keep everything flat, organized, stable. It's a delicate balance. Too many collisions, and particles would clump together, forming larger objects. Too few, and the rings would disperse. But Saturn's rings are in the sweet spot. Enough collisions to stay stable. Not so many that they destroy themselves. It's a system that's been in equilibrium for millions of years. And it's one of the reasons the rings are so beautiful. The rings' ever-changing patterns. From a distance, Saturn's rings look static, unchanging. But up close, they're anything but. The rings are dynamic, constantly shifting and evolving. Small-scale patterns emerge and disappear. Particles clump together, then disperse. Waves propagate through the rings, triggered by the gravity of passing moons. Even the color of the rings changes slightly over time as the angle of sunlight shifts. The Cassini spacecraft revealed this dynamism in stunning detail. Over its 13 years in orbit, Cassini watched the rings change with the seasons. It saw structures that hadn't been visible before. It discovered new ringlets, new gaps, new patterns. The rings aren't a photograph. They're a movie, a constantly unfolding story of gravity and motion. And every time we look, we see something new. The rings of Saturn are a reminder that nothing in the universe is truly static. Everything is in motion. Everything is changing. And that change, that evolution, is part of what makes the universe so fascinating, so endlessly interesting, so worth studying. The mystery of their origin. Where did Saturn's rings come from? It's one of the biggest unsolved questions in planetary science. There are two main theories. The first is that the rings are ancient, formed at the same time as Saturn itself, more than 4 billion years ago. In this scenario, the rings are leftover material from the disk of gas and dust that created Saturn, material that was too close to the planet to form a moon. The second theory is that the rings are young, formed within the last few 100 million years. Perhaps a moon wandered too close to Saturn and was torn apart by tidal forces, or perhaps a collision between two moons shattered them, creating the particles we see today. Both theories have evidence supporting them. The rings' brightness suggests they're young. Old rings would be darker, dirtied by micrometeorite impacts. But the structure of the rings suggests they're old, shaped by billions of years of evolution. It's a puzzle. And we don't have the answer yet. But that's okay. Mysteries are what drive science forward. And Saturn's rings are one of the greatest mysteries of all. The debate over their age. How old are Saturn's rings? Scientists have been debating this question for decades. Some evidence suggests the rings are ancient. Their structure is complex, with gaps and divisions carved out by gravitational resonances. That kind of structure takes time to develop, millions, perhaps billions of years. But other evidence suggests the rings are young. They're too bright, too clean. Over time, micrometeorites should have darkened them, contaminating the ice with dust and rock. The rings should be gray, not bright and white, yet they're still dazzling. In 2017, Cassini made measurements of the ring's mass during its final orbits. The data suggested the rings contain less material than previously thought, and less massive rings would be more easily disrupted. If they're young, that explains their brightness. If they're old, something must be cleaning them, keeping them bright despite eons of impacts. The debate continues. New data, new models, new ideas, and slowly we're piecing together the story. The rings may not reveal their age easily, but we'll keep asking, keep searching, keep trying to understand. The rings that may be disappearing. Here's a sobering thought. Saturn's rings may not last forever. In fact, they may be disappearing right now, slowly, gradually, but inevitably. The rings are losing material. Ice particles are spiraling inward, pulled by Saturn's magnetic field. They fall into the planet's atmosphere, like rain. Scientists call it ring rain, and it's happening constantly. Estimates suggest that the rings are losing material at a rate of about 10,000 kilograms per second. That sounds like a lot, but given the total mass of the rings, it means they could last for another 100 million years, maybe longer, but not forever. Eventually, the rings will fade. They'll thin out, become fainter, until they're gone. It's a reminder that nothing in the universe is permanent. Even the most beautiful things have a lifespan, but that doesn't diminish their beauty. But that doesn't diminish their beauty. If anything, it makes them more precious. Saturn's rings are temporary, a fleeting wonder in cosmic time, and we're lucky to be alive to see them. The rain of ice onto Saturn's surface. The ring rain is a real phenomenon observed by Cassini during its mission. Charged ice particles from the rings interact with Saturn's magnetic field. They become ionized, and the magnetic field pulls them toward the planet. As they spiral inward, they enter Saturn's upper atmosphere. There they vaporize, releasing water vapor and other molecules. The ring rain falls mostly at mid-latitudes, creating faint bands of extra material in Saturn's atmosphere. Scientists can detect it by studying the chemical composition of the upper atmosphere. The presence of water and other ring materials is a telltale sign. The ring rain is part of the ring's evolution. It's how they're slowly disappearing. But it's also a connection between the rings and the planet. Material from the rings becomes part of Saturn. It's absorbed, mixed into the atmosphere, eventually sinking deep into the interior. In a way, the rings are being recycled, returned to the planet they orbit. It's a poetic end for these magnificent structures. Not a destruction, but a transformation, a return home. The rings slowly falling away. Every second, Saturn's rings lose a little more mass. Ice particles fall into the planet. Others are knocked out of orbit by micrometeorite impacts. Slowly, grain by grain, the rings are fading. It's a process that will take millions of years, but it's happening, and there's nothing that can stop it. Eventually, the rings will be too faint to see. They'll become a tenuous halo, invisible except to the most powerful telescopes. And then, someday, they'll be gone entirely. Future astronomers, looking back at our era, might marvel that we got to see Saturn in its full glory, that we lived during the brief cosmic moment when Saturn had rings. But for now, the rings are still here, still bright, still beautiful, and we can still look up or point a telescope toward the sky and see them. It's a privilege, a gift, and a reminder to appreciate the beauty around us, because nothing lasts forever, not even the rings of Saturn. The secrets revealed by the Cassini mission. In 1997, a spacecraft named Cassini launched from Earth. Its destination, Saturn. It would take 7 years to get there, looping through the inner solar system, gaining speed from gravity assists at Venus and Earth, and then making a flyby of Jupiter. In 2004, Cassini arrived, and for the next 13 years, it would revolutionize our understanding of Saturn. Cassini orbited Saturn 294 times. It flew past dozens of moons. It dove through the rings. It measured, photographed, and analyzed every aspect of the Saturn system. The data it sent back filled libraries. The images it captured filled our imaginations. Cassini revealed that Enceladus, a tiny moon, had geysers erupting from its south pole. It showed us the hexagon at Saturn's north pole. It tracked storms, measured magnetic fields, and watched the rings evolve. Cassini was more than a mission. It was a journey, and it changed the way we see Saturn, from a distant, mysterious world to a place we know intimately, a place we've explored. The journey that began in 1997. The Cassini mission was a collaboration between NASA, the European Space Agency. It was one of the most ambitious space missions ever attempted. The spacecraft weighed 6 tons at launch, making it one of the heaviest interplanetary probes ever built. It carried 12 scientific instruments, each designed to study a different aspect of Saturn, and it carried the Huygens probe, a lander built by ESA, to explore Titan, Saturn's largest moon. The journey to Saturn was long, 7 years. Cassini couldn't fly directly. It needed gravity assists to build up enough speed, so it looped through the inner solar system first, twice past Venus, once past Earth, and then a flyby of Jupiter, which gave it the final push it needed. By the time Cassini reached Saturn, it had traveled more than 3 billion kilometers, and its journey was just beginning. The real mission, the exploration of Saturn, would last 13 years, and it would be extraordinary. The spacecraft that changed everything. Cassini was a marvel of engineering. It was powered by radioisotope thermoelectric generators, which converted heat from decaying plutonium into electricity. This was necessary because Saturn is so far from the Sun that solar panels wouldn't generate enough power. The spacecraft had to be robust. It had to survive the harsh environment of space for over a decade. It had to withstand radiation, temperature extremes, and the constant bombardment of micrometeorites. And it did. Cassini exceeded every expectation. It operated for twice its primary mission duration. It made discoveries no one anticipated, and it sent back some of the most beautiful images ever captured in space. Images of Saturn's rings, backlit by the sun. Images of Enceladus's geysers, spraying ice into space. Images of Titan's lakes and rivers. Cassini showed us worlds we'd only imagined, and it did so with grace and precision. When the mission finally ended in 2017, scientists around the world mourned, but they also celebrated. Cassini had done its job, and then some. The flybys of Jupiter and the long cruise on its way to Saturn. Cassini flew past Jupiter. It was December 2000, and Jupiter was perfectly positioned for a gravity assist. Cassini spent months near the giant planet, making observations and capturing images. It studied Jupiter's atmosphere, its magnetosphere, and its moons. The data complemented observations from the Galileo spacecraft, which was orbiting Jupiter at the time. Together, the two spacecraft provided unprecedented views of the Jovian system. But for Cassini, Jupiter was just a waypoint, a brief stop on the long journey to Saturn. After the Jupiter flyby, Cassini entered what mission scientists called the quiet cruise. 4 years of coasting through the empty space between Jupiter and Saturn. The spacecraft was mostly dormant during this time, conserving power and checking its systems. But even during the quiet cruise, Cassini made observations. It studied the cosmic dust environment, it tested its instruments, and slowly, steadily, it approached Saturn. By mid-2004, the ringed planet was looming large, and Cassini was ready. The arrival at Saturn in 2004. On July 1st, 2004, Cassini arrived at Saturn. It was a tense moment. To enter orbit, the spacecraft had to fire its main engine for 96 minutes, slowing down just enough to be captured by Saturn's gravity. If the burn failed, Cassini would fly past Saturn and drift off into the outer solar system. Mission lost, but the burn worked. Cassini slowed down, and it became the first spacecraft to orbit Saturn. The arrival was celebrated around the world. After 7 years of travel, Cassini had reached its destination, and the real mission could begin. Over the next 4 months, Cassini made its first orbits, testing systems, and preparing for the main science campaign. It flew past Titan, Saturn's largest moon, multiple times, and on Christmas Day 2004, it released the Huygens probe, which would descend to Titan's surface 3 weeks later. The arrival at Saturn marked the beginning of one of the most successful planetary missions in history, and for 13 years, Cassini would explore, discover, and inspire. The orbits that revealed the rings in detail. Cassini's orbit around Saturn was carefully designed. It took the spacecraft on a complex path, looping around the planet, diving close to the rings, and flying past moons. Each orbit revealed something new. Close-up views of the rings showed details never seen before. Propeller-shaped disturbances created by tiny moonlets embedded in the rings. Spiral density waves rippling through the particles. The texture and structure of individual ringlets. Cassini flew through gaps in the rings multiple times, sampling the particles and dust. It measured the size distribution of ring particles, their composition, and their interactions. It watched as the rings changed with Saturn's seasons. As the sun's angle shifted, shadows appeared and disappeared. New features emerged from the darkness. Cassini's cameras captured thousands of images of the rings, each one a work of art, each one a piece of scientific data. Together, they transformed our understanding. The rings weren't just beautiful, they were a laboratory, a place to study dynamics, gravity, and the history of the solar system. The Huygens probe and Titan's descent. On January 14th, 2005, the Huygens probe entered Titan's atmosphere. It was a historic moment. The first landing in the outer solar system. Huygens was built by the European Space Agency. It had traveled to Saturn attached to Cassini, and 3 weeks earlier, Cassini had released it on a collision course with Titan. As Huygens descended, it deployed parachutes to slow its fall. Its instruments measured the atmosphere, took photographs, and sampled the chemical composition of Titan's air. The descent took 2.5 hours, and every second was recorded. Huygens sent data back to Cassini, which relayed it to Earth. The probe descended through orange haze, methane clouds, and finally, it emerged into clearer air. Below, Huygens' cameras captured a landscape that looked eerily familiar: valleys, river channels, and a surface littered with rounded stones. Huygens landed on a soft, sandy surface. It survived for 90 minutes after landing, sending back data from the surface. It was a triumph, and it revealed a world unlike any we'd seen before. The first landing in the outer solar system. Titan was mysterious before Huygens. We knew it had a thick atmosphere. We knew there was methane in that atmosphere, but we didn't know what the surface looked like. The atmosphere was too thick, too hazy to see through. Huygens changed that. The images it sent back showed a world that was both alien and familiar. The surface was dark, covered in what looked like organic compounds. The stones, scattered around the landing site, were probably made of water ice, frozen as hard as rock in Titan's frigid temperatures. And there were channels, carved by flowing liquid, not water. Titan is far too cold for liquid water, but methane, liquid methane, flowing across the surface, carving valleys and riverbeds, just like water does on Earth. It was a stunning revelation. Titan had weather. It had rivers and lakes. It had a hydrological cycle, just like Earth's. Only instead of water, it was methane. Huygens' landing was more than a technical achievement. It was a glimpse into a world that mirrors our own, in strange and wonderful ways. The images of Titan's orange sky, as Huygens descended, its cameras captured images of Titan's sky. The sky isn't blue, like Earth's. It's orange, a deep, hazy orange, caused by the thick atmosphere. Titan's atmosphere is denser than Earth's. It's made mostly of nitrogen, like ours, but it also contains methane, and that methane reacts with sunlight to create complex organic molecules. These molecules form a thick haze that envelops the entire moon. The haze scatters light, giving Titan its distinctive color. From the surface, looking up, you'd see an orange glow. The sun would be dim, barely visible through the haze. It would be perpetually overcast, like a foggy day that never ends. But it wouldn't be dark. The haze scatters light in all directions, so even on the surface, there's a soft, diffuse illumination. Huygens' images of the orange sky were haunting. They showed a world that was both beautiful and alien, a place where the familiar rules of atmosphere and light apply, but with entirely different chemistry, a reminder that Earth is just one possibility, and that nature is endlessly creative. The rivers and lakes of liquid methane. Cassini's radar mapped Titan's surface over the course of its mission, and it revealed something astonishing. Lakes, hundreds of them, clustered near the poles. These weren't water lakes. They were liquid methane and ethane, pooled in basins and valleys. Some were small, just a few kilometers across. Others were huge, the size of the Great Lakes in North America. The largest, Kraken Mare, is bigger than the Caspian Sea. These lakes fill and empty with the seasons. Titan's year is 29 Earth years, the same as Saturn's. During Titan's summer, the lakes evaporate. During winter, they fill again with rain. It's a cycle, driven by temperature and sunlight, just like Earth's water cycle, only colder, much colder. Titan's surface temperature is around -180 degrees Celsius. At those temperatures, methane acts like water does on Earth. It evaporates, forms clouds, and falls as rain. It carves channels and fills lakes. Titan has weather, and that makes it one of the most Earth-like worlds we've found. Despite being utterly alien in almost every way, the coldest seas in the solar system. The methane lakes on Titan are the coldest liquid bodies in the solar system at minus 180 degrees Celsius. They're colder than anything on Earth, colder than Antarctica, colder than liquid nitrogen, and yet they're liquid. That's because methane has a very low freezing point. At Titan's temperatures and pressures, it's comfortably above its freezing point. The lakes are calm. There are no waves, at least not large ones. The thick atmosphere dampens any wind that might stir the surface. Cassini's radar showed the lakes as dark, smooth regions, flat and still, but they're not stagnant. The lakes are connected to the atmosphere through evaporation and precipitation, and they're connected to the underground through seepage. Some scientists believe there are aquifers beneath Titan's surface, reservoirs of liquid methane flowing through porous ice. When there's fours of liquid methane flowing through porous ice, it's a hydrological system, just not one we're used to, and it raises fascinating questions. If methane can form lakes and rivers, what else is possible? What other kinds of liquids might exist on other worlds? Titan has opened our minds to new possibilities. The methane rain that falls from orange clouds. On Titan, it rains, not often, but when it does, it pours. The rain is methane, falling from thick orange clouds. The drops are larger than rain on Earth. Titan's lower gravity and thicker atmosphere allow droplets to grow bigger before they fall, and they fall more slowly, drifting down through the dense air like snowflakes. When the rain hits the surface, it carves channels, it fills lakes, it shapes the landscape. Over millions of years, methane rain has sculpted Titan's surface, creating valleys, deltas, and floodplains. Recognizable, familiar weather, but with entirely different chemistry. Scientists have only observed a few rain events on Titan. Cassini caught glimpses of clouds and surface changes that suggested recent rainfall, but Titan's weather is slow. Its seasons last for years. Rain events are rare, but when they happen, they're significant. They reshape the surface, they replenish the lakes, they keep Titan's hydrological cycle running, and they remind us that weather isn't unique to Earth. It's a process that can happen anywhere there's liquid, atmosphere, and temperature variation. The world that mirrors Earth's weather. Titan is the only place in the solar system, besides Earth, with a stable liquid on its surface. That liquid drives a weather cycle. Evaporation, clouds, precipitation, runoff. It's all there. The chemistry is different, the temperatures are different, but the processes are the same. Titan has seasons, driven by its orbit around Saturn. It has equinoxes and solstices. It has summer and winter. During summer, the lakes near the poles shrink. During winter, they grow, just like seasonal lakes on Earth. Studying Titan helps us understand Earth. It shows us that the principles of atmospheric science and hydrology are universal. They don't depend on water. They depend on temperature, pressure, and the properties of liquids and gases. Titan is a laboratory for studying these principles, a place where we can test our theories in an entirely different environment. And in doing so, we learn more about our own planet, about how weather works, about how atmospheres evolve. Titan mirrors Earth, but it also shows us how different Earth-like processes can be when the chemistry changes. The thick atmosphere of Saturn's largest moon. Titan's atmosphere is thicker than Earth's. At the surface, the pressure is about 1.5 times what we experience at sea level. That's similar to the pressure you'd feel at the bottom of a swimming pool. The atmosphere is dense, substantial. You could feel it. And interestingly, Titan's atmosphere is made mostly of nitrogen, about 95%. That's even more than Earth's atmosphere, which is 78% nitrogen. The rest is methane, with traces of other organic compounds. The thick atmosphere is what makes Titan special. It creates weather, it traps heat, and it shields the surface from the harsh radiation of space. Without its atmosphere, Titan would be a frozen, barren rock. But with it, Titan is dynamic, active, interesting. The atmosphere is also opaque. You can't see the surface from space in visible light. You need radar or infrared. That's why Titan remains so mysterious for so long. Its atmosphere hid it from view, but that mystery is part of what makes Titan so fascinating. The hidden ocean beneath Titan's ice. Beneath Titan's surface, there's likely an ocean, not of methane, but of water. Liquid water, mixed with ammonia and salts. This ocean is buried beneath a shell of ice, kilometers thick. We can't see it directly, but we know it's there because of how Titan wobbles as it orbits Saturn. Cassini measured Titan's shape over multiple flybys. The data showed that Titan deforms slightly as it orbits, a phenomenon called tidal flexing. This deformation pattern suggests there's a liquid layer beneath the surface. A solid interior would be too rigid to flex that way. The ocean is probably about 50 to 100 kilometers beneath the surface. It's kept liquid by tidal heating from Saturn and by radioactive decay in Titan's interior. The temperature down there might be just above freezing, cold by our standards, but warm enough for liquid water to exist. This hidden ocean is one of the most exciting discoveries in planetary science, because where there's liquid water, there's the potential for life. We don't know if anything lives in Titan's ocean, but the possibility exists. And that's enough to make Titan one of the most important targets for future exploration. The chemistry that could hint at life. Titan's surface is covered in organic compounds, complex carbon-based molecules created by chemical reactions in the atmosphere. These molecules rain down onto the surface, accumulating over millions of years. The surface is rich in pollens, reddish-brown compounds that form when methane and nitrogen react under ultraviolet light. Scientists have studied these compounds in laboratories, trying to understand their properties and how they form. What they found is fascinating. Pollens are precursors to more complex organic molecules, the building blocks of life. On Titan, these compounds accumulate on the surface, and some of them likely seep down through cracks in the ice toward the subsurface ocean. If they reach that ocean, they could interact with liquid water, and in that interaction, chemistry happens. We don't know if that chemistry leads to life, but it's plausible. Titan has all the ingredients: liquid water, organic compounds, and energy. Whether those ingredients have combined to create life is an open question, but it's one worth asking. And one day we might send a mission to find out. The mystery of Enceladus. Enceladus is a small moon, only about 500 kilometers in diameter. You could fit it comfortably inside the borders of Texas. For years, it was just another icy moon, unremarkable and ignored. But in 2005, Cassini changed everything. During a flyby, Cassini's instruments detected something unexpected: geysers, jets of ice and water vapor erupting from Enceladus' south pole. It was a stunning discovery. This tiny moon was active, not dead, not frozen solid, but alive, with geologic activity. Enceladus became one of the most important targets in the solar system. Cassini flew past it dozens of times, studying the geysers, measuring their composition, and trying to understand what powered them. What Cassini found was even more remarkable than the geysers themselves. Beneath Enceladus's icy shell, there's a global ocean, an entire ocean of liquid water. And that ocean is in contact with the moon's rocky core. Where water meets rock, chemistry happens, and where chemistry happens, life becomes possible. The moon with geysers that touch space. The geysers on Enceladus are extraordinary. They erupt from fractures in the ice near the South Pole, region scientists call tiger stripes. These fractures are warmer than the surrounding terrain, heated by tidal forces from Saturn. The geysers shoot plumes of water vapor and ice particles into space. Some of the material escapes Enceladus entirely, forming a faint ring around Saturn called the E ring. The rest falls back to the surface, coating Enceladus in fresh, bright ice. That's why Enceladus is one of the most reflective objects in the solar system. It's covered in clean ice, constantly replenished by the geysers. Cassini flew through the plumes multiple times, sampling the material. The instruments detected water vapor, ice particles, and organic molecules, simple organics like methane and ethane, but also more complex compounds, molecules that on Earth are associated with life. The geysers are a direct sampling of Enceladus's subsurface ocean, and what they reveal is tantalizing. This little moon has everything needed for life. The ice plumes erupting from its south pole. The plumes are powered by heat, tidal forces from Saturn flex Enceladus as it orbits, generating friction in the moon's interior. That friction creates heat, and that heat melts ice, creating pockets of liquid water beneath the surface. The water is under pressure, and when it finds a crack, a pathway to the surface, it erupts. The plumes are like geysers on Earth, Old Faithful in Yellowstone, Geyser in Iceland, but colder and powered by tidal forces instead of volcanic heat. The plumes are not continuous. They vary in intensity, depending on where Enceladus is in its orbit. When the moon is farthest from Saturn, the tidal forces are weaker and the plumes diminish. When it's closest, the forces are stronger and the plumes increase. Cassini observed this pattern over multiple orbits. It's more evidence that the plumes are linked to tidal heating, and it's more proof that Enceladus is a dynamic, active world. Despite its small size, despite being so far from the sun, Enceladus is alive, and it has secrets still to reveal. The discovery of a subsurface ocean. The discovery of Enceladus's ocean was one of the highlights of the Cassini mission. Scientists pieced together the evidence over years. The geysers were the first clue. Something had to be supplying them with water. Then came measurements of Enceladus's gravity field. As Cassini flew past, it measured tiny variations in the moon's gravity. Those variations suggested a dense region beneath the surface, not ice, which is light, but liquid water, which is denser. The final piece of evidence came from Enceladus's wobble. Like Titan, Enceladus wobbles slightly as it orbits Saturn, and the pattern of that wobble suggested a liquid layer beneath the ice. The ocean is global. It covers the entire moon, buried beneath 20 to 30 kilometers of ice, and it's in contact with the rocky core. That contact is crucial. It means minerals from the rock can dissolve into the water, providing nutrients, and it means there's a source of chemical energy. On Earth, hydrothermal vents on the ocean floor support entire ecosystems. Could the same be true on Enceladus? We don't know, but we're looking. The organic molecules in its spray. When Cassini flew through Enceladus plumes, its instruments detected organic molecules. These weren't just simple compounds. There were complex molecules, chains of carbon and hydrogen, nitrogen-bearing compounds, even molecules that on Earth are associated with biological processes. The organics don't prove there's life on Enceladus. They can form through non-biological chemistry, but they're a good sign. They show that Enceladus has the raw materials for life: carbon, hydrogen, nitrogen, oxygen, all the elements needed to build living organisms. The concentration of organics in the plumes was surprising. It suggests there's active chemistry happening in Enceladus's ocean. Reactions between water and rock, dissolution of minerals, possibly even hydrothermal activity. The more we learn about Enceladus, the more interesting it becomes. It's not just a frozen moon. It's a potential habitat, a place where life might exist right now, in the dark waters beneath the ice. And that makes Enceladus one of the most important targets for future exploration. The possibility of life beneath the ice. Could there be life on Enceladus? It's one of the most exciting questions in astrobiology. Enceladus has liquid water. It has organic compounds. It has a source of energy. in the form of tidal heating and chemical reactions. Those are the three ingredients for life as we know it. On Earth, wherever we find liquid water, we find life, even in the most extreme environments. Deep-sea hydrothermal vents, Antarctic ice sheets, acidic hot springs. Life finds a way. Enceladus ocean is cold, dark, and buried beneath kilometers of ice. But it's not that different from Earth's deep oceans. And those oceans are teeming with life. We don't have proof that life exists on Enceladus. We'd need to go there, sample the ocean directly, and look for signs of biology. But the conditions are right, and that's enough to hope. Enceladus has taught us that habitability isn't limited to planets in the Goldwater zone. It can exist in the most unexpected places. Small moons, far from the sun, heated by tidal forces. The universe is full of surprises, and Enceladus is one of them. The tiny moon that redefined habitability. Before Enceladus, scientists thought habitability required sunlight. A planet needed to be in the Goldilocks zone, where temperatures were just right for liquid water. But Enceladus changed that thinking. Here's a moon smaller than most asteroids, orbiting a gas giant nearly 10 times farther from the sun than Earth. And yet, it has a liquid ocean. It has chemistry. It has energy. It's potentially habitable. Enceladus, along with other icy moons like Europa, has expanded our definition of where life might exist. It's not just about distance from the sun. It's about internal heat, tidal forces, chemical energy. There might be habitable worlds throughout the galaxy, far from their stars, heated from within, worlds we'd never have considered before. Enceladus is small, but its impact on astrobiology has been enormous. It's redefined what's possible, and it's given us hope that life might be more common than we ever imagined, hiding beneath the ice, waiting to be discovered. The other moons of Saturn. Saturn has at least 145 known moons. Most are small, irregular chunks of rock and ice, but several are large enough to be interesting, to have their own geology, their own stories. Titan and Enceladus get most of the attention, but they're not alone. There's Mimas, with its giant crater that makes it look like the Death Star. There's Iapetus, half bright and half dark, like a yin-yang symbol. There's Rhea, the second largest moon, covered in ancient craters. And there are dozens of smaller moons, some orbiting within the rings, some wandering in the outer reaches of Saturn's gravitational influence. Each moon is unique. Each has its own history, and together they form a complex, fascinating system, a miniature solar system, with Saturn at its center. Exploring these moons has been one of the great achievements of the Cassini mission, and each discovery has revealed new surprises, new mysteries, new reasons to keep exploring. The icy worlds orbiting in harmony. Saturn's major moons are locked in a delicate gravitational dance. Their orbits are interconnected, shaped by resonances and interactions. Titan, the largest, dominates. Its gravity influences many of the smaller moons. Some moons share orbits. Others swap places in a cosmic dance choreographed by gravity. This harmony isn't random. It's the result of millions of years of evolution. Collisions, migrations, and gravitational tugs have shaped the system into what it is today. The moons pull on each other, on the rings, on Saturn itself. And those forces create tides, generate heat, and shape surfaces. It's a system in balance, but it's not static. It's constantly evolving, constantly changing, and studying these interactions helps us understand how planetary systems form and evolve, not just around Saturn, but around stars across the galaxy. Saturn's moons are a laboratory, a place to study dynamics, resonances, and the long-term evolution of complex systems. The shepherd moons that guard the rings. Some of Saturn's smallest moons orbit within or near the rings. These shepherd moons, as they're called, play a crucial role in maintaining the ring's structure. Pan orbits within the Encke gap in the A-ring, Its gravity clears a path, keeping the gap open. Daphnis does the same in the Keeler Gap. Prometheus and Pandora orbit on either side of the F ring, hurting the particles and keeping them confined. These moons are tiny. Pan is only 35 kilometers across. Daphnis is even smaller, just 8 kilometers. But their influence is significant. Without them, the gaps would fill in. The rings would spread out, losing their structure. The shepherd moons are like gardeners, maintaining order in the chaos. They're proof that even small objects can have a big impact, that gravity, no matter how weak, always matters, and that the rings of Saturn are not just beautiful, they're a precisely tuned system, held together by forces we're only beginning to understand. The chaotic orbits of Janus and Epimetheus. Two of Saturn's moons, Janus and Epimetheus, share the same orbit, almost. They orbit at nearly the same distance from Saturn. Their paths separated by only about 50 kilometers, and every 4 years, they swap places. Here's how it works. The inner moon orbits slightly faster than the outer one. Slowly, it catches up. When they approach each other, their gravitational interaction causes them to exchange orbital energy. The inner moon moves outward. The outer moon moves inward, and they continue on, now in each other's former orbits. It's a dance, a gravitational waltz, and it's stable, at least for now. Scientists believe this arrangement formed after a collision between a larger moon, which broke into fragments. Janus and Epimetheus are the two largest fragments, still orbiting close to where the original moon once was. Their dance is a reminder that orbits aren't fixed, they're dynamic, and sometimes the universe choreographs something truly elegant. The shadowed surface of Mimas, the Death Star moon. Mimas is famous for one feature, the Herschel crater, a massive impact crater that covers nearly a third of the moon's diameter. The crater has a central peak that rises 6 kilometers above the floor, and when seen from the right angle, it makes Mimas look uncannily like the Death Star from Star Wars. The resemblance is pure coincidence. Star Wars came out in 1977. Mimas crater was discovered in 1980 by Voyager 1, but the similarity is striking, and it's made Mimas one of the most recognizable moons in the solar system. The impact that created Herschel must have been enormous. It nearly shattered Mimas. The shock waves from the impact created fractures on the opposite side of the moon. Mimas survived, but just barely. Now it orbits Saturn, a testament to the violence that shaped the early solar system, and a reminder that even the most innocuous-looking moons have dramatic histories. The ridges of Iapetus, half dark and half bright. Iapetus is one of the strangest moons in the solar system. One hemisphere is bright, covered in clean ice. The other is dark, coated in a reddish-brown material. The boundary between the two is sharp, creating a yin-yang pattern that's visible even from Earth. Scientists aren't entirely sure why Iapetus looks this way. The leading theory is that the dark material comes from another moon, possibly Phoebe. Dust from Phoebe spirals inward and coats the leading hemisphere of Iapetus. Over time, sunlight warms that material, causing ice to sublimate. The dark material is left behind, darkening the surface further. But Iapetus has another mystery. A ridge, a massive equatorial ridge that circles half the moon. It's 20 kilometers wide and 13 kilometers high in places. No one knows how it formed. Some theories suggest it's the remnant of a collapsed ring. Others think it's related to ancient tectonic activity. Iapetus is full of mysteries, and it's one of the most intriguing targets for future exploration. The twisted dance of Tethys and Dione. Tethys and Dione are mid-sized icy moons, orbiting Saturn in a gentle resonance. For every 2 orbits Dione completes, Tethys completes 3. This ratio keeps their orbits stable, preventing close approaches that might destabilize the system. Both moons are heavily cratered, evidence of a violent past, but they also show signs of internal activity. Tethys has a massive canyon system called Ithaca Chasma, stretching across nearly 3/4 of the moon's circumference. It may have formed when Tethys's interior froze and expanded, cracking the surface. Dione has bright, wispy features on its trailing hemisphere. For years, scientists thought these were surface deposits, but Cassini revealed they're actually cliffs and fractures, reflecting sunlight at different angles. Both moons are geologically interesting, and their orbital dance ensures they'll remain stable for millions of years to come. It's a partnership, a gravitational relationship that's lasted since the solar system was young. The hidden complexity of Rhea. Rhea is Saturn's second largest moon. It's heavily cratered, ancient, and at first glance, relatively boring. But Cassini revealed hidden complexity. Rhea has a tenuous atmosphere, made of oxygen and carbon dioxide. It's extremely thin, barely there, but it exists, possibly created by radiation from Saturn's magnetosphere, breaking apart ice on the surface. Cassini also detected what might be a debris ring around Rhea, a faint disk of dust and ice particles orbiting the moon. If confirmed, it would make Rhea the only moon in the solar system with rings of its own. The evidence isn't conclusive yet, but it's tantalizing. Rhea also has strange bright rays emanating from some craters, features that suggest relatively recent impacts. And its interior may be partially differentiated, with a small rocky core beneath the ice. Rhea is a reminder that even the most ordinary-looking moons can surprise us, that there's always more to discover, more questions to ask. The outer moons that wander in the dark, beyond the major moons. Saturn has dozens of irregular moons. These are small, distant objects, probably captured asteroids or comets. They orbit far from Saturn, many in retrograde, going the opposite direction of the planet's rotation. These moons have strange, elongated orbits. Some take years to complete a single trip around Saturn. They're not part of the inner system, not connected to the rings or the major moons. They're wanderers, captured by Saturn's gravity long ago. They now drift in the outer darkness. Most of them are unnamed, just designations, numbers and letters. But each one has its own story. Each one is a piece of the early solar system, preserved in the cold. Studying these outer moons helps us understand how planetary systems evolve, how planets capture objects, how the solar system looked billions of years ago. They're small, insignificant on their own, but together they tell a story, a history written in orbits and ice. The 145 known moons of Saturn. Saturn has more known moons than any other planet in the solar system, at least 145, though the number keeps growing. Some are large, like Titan and Rhea. Others are tiny, just a few kilometers across. Many were discovered recently, using powerful ground-based telescopes and data from Cassini. The moons come in all shapes and sizes. Some are round, shaped by their own gravity. Others are irregular, lumpy chunks of rock and ice. Some orbit close to Saturn, within the rings. Others orbit millions of kilometers away. Each moon is unique. Each has its own composition, its own history, and together, they form one of the most complex satellite systems in the solar system. We've only explored a fraction of these moons in detail. Cassini focused on the largest and most interesting, but there are dozens more waiting to be studied, each one a world unto itself, each one with secrets waiting to be discovered. The constant discovery of more. Every few years, astronomers discover new moons around Saturn. They use large telescopes, sophisticated imaging techniques, and careful analysis to spot tiny objects in orbit around the giant planet. Some of these moons are only a few kilometers across. They're faint, barely visible, but they're there, and each discovery adds to our understanding of the Saturn system. The number of known moons has grown steadily over the decades. In the 1980s, we knew of fewer than 20. By the 2000s, that number had doubled. Now it's over 145, and there are likely more waiting to be found. Each new moon raises questions. Where did it come from? Is it a captured object? Or did it form with Saturn? How does it interact with the other moons? With the rings? Discovery is just the beginning. Each new moon is a puzzle, and we're slowly putting the pieces together. The balance of gravity that holds them all. Saturn's system is held together by gravity. The planet's immense mass dominates, keeping moons in orbit, pulling on the rings, shaping everything around it. But it's not just Saturn's gravity. The moons pull on each other. They create resonances, stabilize orbits, and sometimes disrupt them. The rings interact with the moons, transferring momentum and energy. It's a complex, interconnected system, a web of gravitational interactions that spans millions of kilometers. And it's stable, at least for now. The orbits are predictable. The system is in equilibrium. But that equilibrium is dynamic. It's constantly adjusting, constantly evolving. Over millions of years, the system will change. Moons will drift. Resonances will shift. The rings will fade. But for now, everything is balanced, held together by invisible forces. A reminder that gravity isn't just a force, it's the architect of the cosmos, and Saturn's system is one of its masterpieces. The subtle pull of Saturn's magnetosphere. Saturn's magnetic field extends far into space, creating a vast magnetosphere. This invisible bubble shields Saturn and its moons from the solar wind, but it also interacts with the moons in subtle ways. Charged particles trapped in the magnetosphere bombard the surfaces of moons like Dione, Rhea, and Enceladus. These particles break apart water ice, releasing oxygen and creating tenuous atmospheres. The magnetosphere also channels particles from Enceladus plumes towards Saturn, creating auroras at the poles. The interactions between the magnetosphere and the moons are complex. They involve plasma physics, magnetic field lines, and electric currents. Scientists are still unraveling the details. But what's clear is that Saturn's magnetosphere is more than just a shield. It's an active participant in the system, shaping surfaces, creating atmospheres, and connecting Saturn to its moons in ways we're only beginning to understand. The planet's invisible force field, Saturn's magnetosphere, is massive. It extends millions of kilometers into space. At its farthest reach, it's larger than the Sun. Inside this bubble, Saturn's magnetic field controls the behavior of charged particles. Electrons and ions from the solar wind are deflected, unable to reach the planet. But some particles are trapped, spiraling along magnetic field lines. They form radiation belts, similar to Earth's Van Allen belts. These belts are intense. Any spacecraft passing through them is bombarded with radiation. Cassini had to navigate carefully, timing its orbits to minimize exposure. The magnetosphere also interacts with Saturn's rings and moons. It creates electric currents, generates radio emissions, and shapes the distribution of charged particles. It's an invisible structure. We can't see it with our eyes, but we can measure it, map it, and study its effects. And in doing so, we learn about the fundamental processes that govern planetary magnetic fields throughout the universe. The radio emissions that sing through space. Saturn emits radio waves, not random noise, but structured emissions, bursts of energy that sweep across the radio spectrum. These emissions are called Saturn kilometric radiation, or SKR. They're generated by the interaction between charged particles and Saturn's magnetic field. As particles spiral along field lines, they emit radiation. The emissions vary with Saturn's rotation. They pulse, like a cosmic lighthouse. Scientists use these pulses to measure Saturn's rotation rate. But there's a mystery. The rotation period, measured from the radio emissions, has changed over time. It's not constant. No one knows why. It's possible the magnetosphere itself is rotating at a different rate than the planet. Or perhaps the emissions are influenced by the solar wind. It's one of the many puzzles surrounding Saturn. But the radio emissions are also beautiful. If you could hear them, they'd sound like whistles and chirps. a song from the depths of space, a reminder that the universe is filled with signals, waiting to be heard. The strange auroras, seen from Cassini. Saturn's auroras are some of the most spectacular phenomena in the solar system. They glow at the poles, driven by charged particles from the solar wind and from Enceladus's plumes. The auroras are enormous. The oval at the North Pole is larger than Earth, and they're bright, glowing in ultraviolet light. Cassini captured images of the auroras over many years. The images showed how the auroras change with time. They brighten during solar storms, when the solar wind intensifies. They shift and shimmer, following the magnetic field lines, and they're connected to Enceladus. Material from the moon's geysers becomes ionized and is funneled toward the poles. When it hits Saturn's atmosphere, it creates a bright spot, a footprint of Enceladus on Saturn itself. The auroras are more than just beautiful lights. They're a window into the interactions between Saturn, its moons, and the solar wind. They reveal the complexity of the system, and they remind us that even in the cold, dark reaches of the outer solar system, nature creates beauty beyond measure. The shadows of the rings crossing the poles. As Saturn orbits the Sun, its tilt changes. The rings, which are aligned with Saturn's equator, cast shadows on different parts of the planet. During the equinox, when the Sun is directly over the equator, the rings cast no shadow, but during other times of the year, the shadow sweeps across the planet. The shadow is dark, a stark band cutting across Saturn's clouds. It moves as Saturn rotates, creating a dynamic pattern. Near the poles, the shadow becomes more pronounced, stretching toward the pole itself. Cassini captured images of these shadows over the course of its mission. They showed how the lighting changed with the seasons, and they revealed details in the rings that weren't visible before. When the Sun is low, it creates long shadows that highlight structures in the rings. Tiny moons cast shadows. Gaps become more visible. It's like how a low sun on Earth highlights textures and details. Saturn's shadows are more than just beautiful. They're informative, and they add depth and drama to images of the ringed planet. The seasons of Saturn's long year. Saturn's year is 29 Earth years long. That's how long it takes to complete one orbit around the Sun. And because Saturn's axis is tilted, like Earth's, it experiences seasons, long, slow seasons that last over 7 Earth years each. During Saturn's summer, one pole is tilted toward the Sun. That hemisphere receives more sunlight. Temperatures rise slightly. The atmosphere changes. Storms become more active. During winter, the opposite pole is tilted away. That hemisphere is in darkness. Temperatures drop. The atmosphere becomes calm. The rings cast shadows that shift with the seasons. During equinox, the rings are edge-on to the Sun. They nearly disappear when viewed from Earth. But during the height of summer or winter, the rings are fully illuminated. Saturn's seasons affect everything: the weather, the moons, even the rings. Cassini arrived at Saturn near the end of southern summer. By the time the mission ended, northern summer had begun. Cassini witnessed the transition, a changing of the seasons on a world far from home. The 29-year journey around the Sun. Saturn moves slowly through space. It's far from the Sun, and its orbit is vast. At an average distance of 1.4 billion kilometers, it takes nearly 30 years to complete one lap. That's a long journey. During that time, the Sun appears as a distant point of light, small, cold, far away. Saturn receives only a fraction of the sunlight that Earth does. But that's enough. It's enough to drive the weather, to power the seasons, to illuminate the rings. The long year means that each season on Saturn lasts about 7 Earth years. If you lived on Saturn, you'd experience 7-year winters, 7-year springs, 7-year summers. Everything would happen slowly. Storm seasons would last for years. The migration of clouds across hemispheres would be a multi-year process. Saturn's long year is a reminder of the vastness of the outer solar system, of the immense distances involved, and of the patience required to study worlds so far from home. The changing light on its rings. As Saturn orbits the Sun, the angle of sunlight hitting the rings changes. During equinox, the Sun shines directly along the plane of the rings. The rings appear thin, almost invisible. Shadows cast by structures in the rings become long and dramatic. It's a brief period, lasting only a few months, but it's a spectacular time to observe Saturn. Outside of equinox, the rings are tilted toward or away from the Sun. They catch the light, glowing brightly. The angle changes how we see the rings from Earth. When the rings are fully open, they're at their most impressive. Spread wide, reflecting sunlight, they dominate Saturn's appearance. When they're edge-on, they vanish, and Saturn looks naked, almost incomplete. The changing light reveals different features. During equinox, vertical structures become visible. Moonlets embedded in the rings cast shadows, revealing their presence. During other times, the overall structure and brightness of the rings takes center stage. The light is always changing, and Saturn is always revealing something new. The tilt that creates its seasons. Saturn's axis is tilted about 26.7 degrees relative to its orbit. That's similar to Earth's tilt of 23.5 degrees. And like Earth, that tilt is what creates seasons. As Saturn orbits the Sun, different hemispheres are tilted toward or away from the sunlight. When the northern hemisphere is tilted toward the Sun, it experiences summer. When it's tilted away, it experiences winter. The tilt also affects the rings. Because the rings lie in Saturn's equatorial plane, they tilt with the planet. During northern summer, the rings are tilted toward the Sun. Southern summer tilts them the other way. At equinox, they're edge-on. Saturn's tilt is stable, maintained by the planet's angular momentum. It's been the same for billions of years, and it will likely remain the same for billions more. That stability creates predictable seasons, a rhythm that's been going on since Saturn formed. And it's one of the many factors that make Saturn such a fascinating world to study. Predictable, yet always changing. The eclipses seen from the giant. From Saturn, eclipses are common. The planet has over 100 moons, and many of them pass in front of the Sun, casting shadows on Saturn's clouds. These are solar eclipses, just like on Earth, but they're more frequent, almost daily. The largest moon, Titan, casts the biggest shadows. When Titan passes between Saturn and the Sun, its shadow races across Saturn's surface. A dark spot, hundreds of kilometers wide, moving with Titan's orbital speed. Cassini captured images of these eclipses. The shadows are crisp, well-defined, and they reveal details in Saturn's clouds. The contrast between shadow and sunlight highlights structures that would otherwise be difficult to see. From the surface of one of Saturn's moons, watching an eclipse would be a common sight. The Sun is small from that distance, just a bright point, and when a moon passes in front, it would dim briefly, then return. A cosmic reminder that you're part of a vast system, orbiting a giant planet far from home. The grand finale of the Cassini mission. In April 2017, Cassini began the final phase of its mission, the grand finale. For 13 years, Cassini had orbited Saturn, making discoveries and capturing images. But its fuel was running low, and the mission had to end. Rather than let Cassini crash into one of Saturn's moons, possibly contaminating them with Earth microbes, mission controllers decided on a different plan. They would send Cassini diving between Saturn and its rings, a region no spacecraft had ever explored. It was risky. No one knew what the environment was like in that gap. Would Cassini be destroyed by ring particles? Would the radiation be too intense? But it was worth the risk. The data would be invaluable. And so Cassini dove. 22 times it plunged through the gap, skimming just above Saturn's cloud tops. The spacecraft survived, and the data it sent back was extraordinary. Measurements of Saturn's magnetic field, images of the rings from unprecedented angles, and insights into the planet's interior structure. The dive between the rings and the planet. The gap between Saturn's rings and its atmosphere is only about 2,000 kilometers wide. That might sound like a lot, but at the speeds Cassini was traveling, it passed through the gap in minutes. Each dive was a heart-stopping moment. Mission controllers couldn't communicate with Cassini in real time. The signals took over an hour to reach Earth. By the time they knew if Cassini had survived, the dive was already over. But Cassini kept going, dive after dive. Each one took it closer to Saturn's clouds. The spacecraft measured the planet's gravitational field with unprecedented precision. It sampled the thin atmosphere at the edge of space, and it looked down at the rings from above, seeing structures never visible before. The grand finale was a triumph, a final hurrah for a mission that had already exceeded all expectations. And it provided data that scientists are still analyzing today. Data that's helping us understand Saturn in ways we never could before. The final signal sent from the end of all journeys. On September 15th, 2017, Cassini's journey ended. Its fuel exhausted, the spacecraft began its final descent into Saturn's atmosphere. Mission controllers watched as Cassini's signal grew weaker. The spacecraft was tumbling, its thrusters firing desperately to keep its antenna pointed at Earth. But it was a losing battle. Saturn's gravity pulled Cassini down, deeper, faster. The atmospheric pressure increased. The heat intensified. Cassini's instruments kept transmitting data, right up to the end. And then, the signal stopped. Cassini was gone, vaporized in Saturn's upper atmosphere. It became part of the planet it had studied for 13 years. The end of Cassini was bittersweet. It was the end of an incredible mission, but it was also a fitting conclusion. Cassini had given us Saturn. It had shown us the rings, the moons, the storms, and the mysteries, and in the end, it became one with the planet. A final gift, a final contribution to the world it had explored so thoroughly. Cassini's legacy lives on, in the data, in the images, and in the countless discoveries yet to be made from the information it sent home.